Hello, this video is called the Improved Performance Research Integration Tool, or IMPRINT, Maintenance Modeling. IMPRINT stands for the Improved Performance Research Integration Tool. It is a manpower, personnel, and training prediction tool owned by the U.S. Army Laboratory and developed by Alion Science and Technology. IMPRINT provides the means for estimating manpower, personnel, and training requirements and constraints for new weapon systems early in the acquisition process. It is freely available to U.S. Department of Defense employees and contractors. IMPRINT contains 4 modules that each support different human performance analyses. In this video, I'm going to provide an introduction to the maintenance module in IMPRINT. Why should you use the maintenance module? The maintenance module allows users to estimate the maintenance manpower requirements, dependent on the system maintenance parameters and the system operational profile, all of which can be varied using the IMPRINT maintenance module. The maintenance module was designed to answer questions such as those listed on this slide. Has the operational readiness been achieved? Will systems be available to deploy when scheduled? How many people of each specialty are required to meet the system availability requirement? IMPRINT allows you to run the model with or without crew limits. Running without imposing crew limits shows a maximum number of warfighters of each specialty required. Which pieces of equipment and maintenance tasks are the high drivers for maintenance? Where should investments be made to get the most bang for the buck? How should each organizational level be staffed? Maintenance can be formed at the unit level, in a nearby facility, or by a mobile repair team. How many warfighters are needed across each organization? How sensitive is my maintenance manpower requirement to the failure rate of individual components? IMPRINT lets you define multiple scenarios to play what if with mission parameters. Let's now go into IMPRINT and open a new maintenance model. This is what IMPRINT looks like when you first open it. You'll see there's a start page that's showing. To start a new maintenance model, you simply find the new maintenance model icon, click on it, and IMPRINT will create a new maintenance model. You'll see that in the analysis tree, there's now a new node called maintenance model with one scenario beneath it. So now you can begin entering your maintenance parameters. If you right-click on scenario, you can add new segments. If you right-click on maintenance models, you can add a new scenario or a new system. Next, I'm going to open an existing model to show you all of the parameters in a maintenance model. Now I'm going to open an existing model from the IMPRINT start page. So you can see on the start page I've got a list of recent models over here. So I'm going to open this multi-system model 10-day run. So now you can see it's loaded my model. It's got the name of the model up here in the title bar. I've expanded my maintenance model node, showing my systems and my scenarios. So now I'm ready to edit or view any of my maintenance model parameters. I could also open a recent file from the File menu, going down here and saying Recent, or I can just say Open Analysis and it'll open the standard File Open dialog where you can navigate to any folder where your analysis is and open it from there. The IMPRINT interface is shown on this slide. It has many features similar to other Windows applications. By default, there is a menu bar, toolbar, analysis tree, message bar, properties window, descriptor window, and output window. The environment is user configurable. You can move, resize, hide, and unhide various components as you desire. There are 3 elements that must be defined for any maintenance model. The first is warfighters. You need to define the specialties that will be maintaining the equipment. The second is the systems. You need to define what systems are used in the scenarios and what are the associated preventative, corrective, and scheduled maintenance parameters. The third is the scenarios. What are the operational and logistic profiles? We'll now go back to IMPRINT and expand our warfighters node in the analysis tree to be able to see the specialties. So now I'm going to expand my warfighter node in my analysis tree just by clicking that plus sign. You'll notice there are 3 nodes below the warfighters. For the maintenance module, we focus on the maintainers and the supply and support personnel. If I click on the maintainers node to expand it, I can see all the specialties that are available in this model. To add a new maintainer, I just right-click on maintainer, say new maintainer. A new window will pop open that lets me specify the specialty for this new maintainer. So I can pick, let's say, an 11 Bravo. I say OK, and that specialty then gets added to my maintainer list. Next, I will go over how systems are represented in the IMPRINT. Systems are the equipment used by the warfighters in the scenario. They require maintenance to be performed on them to remain operational. Examples would be a tank, a helicopter, or a truck. To see what systems have been defined, just expand the Systems node under the Maintenance modules. Let's go to IMPRINT and try it. So now back in IMPRINT, we're going to see what systems have been defined. So to do that, we just expand our Systems node by clicking the plus sign next to Systems. And you can see that this particular analysis has 3 different types of system. It's got a cargo helicopter, a light truck, and a tank. Systems are made up of one or more subsystems. In the example shown, the subsystems are armament, turret structure, communications, the engine, and suspension and tracks. To view the subsystems, we expand the System node. Let's go to IMPRINT and try it. So back in IMPRINT, I can see all the subsystems by expanding any of the System nodes. For example, if I click the plus sign next to the tank, I can then see all the subsystems associated with the tank. To collapse it back up, I just hit the minus sign. And same thing for any other system. If I click the plus sign next to the light truck, it's going to expand and I can see its subsystems. Subsystems are in turn made up of components. In this example, the 2 components are the cannon tube and the cannon breech. Components are the elements that have maintenance performed on them. You expand the Subsystem node to view the components. To see the components, you just expand any of the subsystems. So here is my tank system, my armament subsystem. If I expand that, clicking on the plus sign, I can see there's 4 components. I can move this over here so you can see them all. So I've got armament other, armament scheduled maintenance, breech, and cannon tube. Components have maintenance actions performed on them. Repair tasks are things like adjust and repair, inspect, remove and replace, test and check, or troubleshoot. They can be preventative, corrective, or scheduled. Expand any component to view the repair tasks. To see the repair tasks, I just expand any component. So here is my tank system, my armament subsystem. I'm going to expand my component armament other, and I can see that there's 2 maintenance tasks associated with it. Adjust and repair, and remove and replace. Double-click on a repair task to view or edit its parameters. If I double-click on the adjust and repair task, the description window opens in the middle. From here, I can change its name. I can set its maintenance action. So I've selected adjust and repair, but I can inspect it, I can rebuild, I can remove, etc. I can set its usage units from miles, rounds, or hours. I can set the maintenance type of either preventative, corrective, or scheduled. Then down below there's 2 tabs, Info and Timing. On the Info tab, I specify what specialties are used to perform the maintenance, and I can specify up to 2. And for each one, I need how many of those type are needed to perform the maintenance. So in this case, I only need 1 specialty, and I only need 1 person. Down below here is location information, so I specify what org level. Is it org, DS, or GS? Is it on or off equipment? Is a contact team used? Is a crew chief used? And then down below there, I finally enter a chance of critical system failure as a percentage. So this one has 7% chance of system critical failure. And then I can say whether I'm going to need to wait for spares or not. On the Timing tab, that's where I enter the component failure and repair time data. So here's my component failure, or my mean operational units between failure. I can pick a distribution, and then based on that I would enter a number. So in this case, my task is going to have to happen about every 79 hours. And then the time to repair it once it's broken is a mean of 1.01 hours with no standard deviation. Another nice thing is if I want to see all of the repair tasks associated with a component, I can just double click on the component level. So here for my armament other, I can see there's 2 repair tasks, and I can edit any of these parameters from here. Also, double clicking on a system, so if I move up here and double click on armament, then I can then see all of the components and all of the repair tasks for all of those components. If I go up to the system level and double click there, then I can see the repair tasks, the subsystems, and the crew maintainers. Data can be entered from any of these grids. To summarize, in IMPRINT, the first step of the maintenance manning analysis is the decomposition or breakdown of the system of interest into its major subsystems, and then the decomposition of subsystems into their components. This information taxonomy is considered the way the U.S. military describes systems currently. In fact, it's consistent with the Standardized Logistics Support Analysis Reports, or LSAR, of which IMPRINT can take as a direct import. Then, the task or set of tasks that will need to be performed on each component at some time is defined. Each task is further described as either corrective maintenance, preventative maintenance, or scheduled maintenance. The third component of a maintenance model are the scenarios. Scenarios are the conditions under which the system and its components will be used. The scenario may contain several segments or time deployments of specific numbers of systems, each drawing from the same pool of resources for repairs. Once the system has been fully described, its subsystem, component, task, and all the associated repair task data, the mission scenario or scenarios expected for that system must be described. By building multiple scenarios, mission-specific manning levels can be determined. The elements of a scenario are the operational system profile, what are the available systems and segments, the available maintenance crew and contact team, that is, the number and types of people available to do the maintenance on each shift, the travel time on the battlefield, which describes the amount of time to get the system to the people, or the people to the system, the likelihood that repair parts are available, and if they're not available, the average wait time, fuel and ammo supply data. Like all of the data elements in IMPRINT, the scenario data elements can be varied. After examining the output of one model run, it might be informative to vary the number of people available on a shift, or increase the distances traveled to better represent the increased size of the future battle space. Or you can increase the repair parts availability to represent alternative supply systems. Scenarios appear below the systems in the analysis tree. In this analysis, there's one scenario, and it's called 10 Days of Missions. To view the scenario properties, double-click on the node. When I double-click the scenario, a description window opens. So I'm going to double-click on 10 Days of Missions. Here's my description window. From here, I can enter a name, 10 Days of Missions. I can enter a description. For this one, I've left it blank. But then down below, there are 8 different tabs where I can enter data. First tab is Available Systems, and this allows me to designate the number of systems that are available across the scenario. Multiple system types may be included in the same maintenance model, so I need to specify the availability of each type. In this particular model, I have one of each type. The Segment tab lists all defined segments in the scenario. In this case, we only have one called Mission 1. The Fuel Supply option lets me factor in suppliers and supporters into the manpower requirement estimates. Here I can enter the name, the associated system, capacity, load time, maximum daily trips, and the specialties needed. The greater number of trips a single transporter can make, the fewer number of additional transporters or transporter operators are required. Load time affects the man hours required by the supply and support personnel to man this transporter. The next tab is the Ammo Supply tab. It is similar to the Fuel Supply tab, and it helps factor suppliers and supporters in the manpower requirements. Here I enter the name, associated system, capacity, load time, max daily trips, and specialties needed. The travel time is the time it takes for a system to travel from the point of breakdown to a repair facility, or for a contact team to travel from a point of dispatch to the point of breakdown. The required time is added to the total time to repair in order to accurately reflect system availability. The different organizations are org, or organizational support, where maintenance can be done at the unit level. These repairs are always done on the system. DS is direct support, where the repair team is located typically at a facility nearby. Entire systems can be taken to this facility or specific parts. GS is general support, where the maintenance facility is located remotely from the system and only parts can be sent to the facility. Contact team, a mobile repair team goes out to the system to do repairs, and if a system is flagged for crew chief, any operator of that system, which is specifically designated as a maintainer, may repair that task. The next tab is Spares. This affects system availability. If a system has spare parts readily accessible, it may be returned to service sooner than when a system that must wait for a spare part. Numbers displayed in the percent available column indicate the percentage of time spare parts required by the subsystem are available. The numbers in the wait time hours indicate the number of hours the system must wait for spare parts to arrive. In this example, all spare parts are available. This enables the crew manning the system to do repairs and not have to wait for spares. The next tab is Maintenance Crew. It helps establish crew constraints. When a crew is limited, fewer systems are likely to be sent out and fewer systems are likely to be immediately repaired. As a result, operational readiness may be affected. So for each specialty here, you enter the shift time in hours. Each shift is 12 hours. Determine the number of shifts in a 24-hour period. In this case, 2 shifts will be manned. The maintenance shift level whose data you are entering. Note, when you are finished entering data for one level, select the next level to add its corresponding data from the drop-down up top here. A quantity column appears for each shift where you can add in the event you want to vary the maintainers by shift. In this example, we have 999 maintainers of specialty type 45E in grade 20 for each shift. At least one of the repair tasks defined for our system requires 4 of these maintainers at a minimum. So here's our minimum right here. This is the most required by a single task and is referred to as the minimum crew. Contact team is the last tab. It's a mobile repair team that travels out to the system to do repairs. Here you enter the number of contact teams that will be shared by all systems in this scenario. In this example, there is 1 contact team to cover all systems. There are 2 multifunctional maintainers on each contact team, and only 3 repair actions at any one time can be in the queue waiting for the contact team attention. At such time, any subsequent maintenance actions must be routed to other maintenance levels. Segments are scheduled deployments which establish usage of specific numbers of systems. This usage possibly leads to component failure. In the example shown here, there are 3 segments. Each starts at a different time and different numbers of systems are sent out with each segment. The operational profile data items are where the expected op tempo or operational tempo is represented for a scenario. There are 3 sets of data associated with the operational profile: usage data, time and systems data, and combat data. The distances traveled and the number of rounds fired describe the intensity of the mission. For example, a training mission may require only short distances and no live firings of ammunition. On the other hand, a combat scenario may have greater distances and quite possibly a large number of rounds fired. The time and systems data allow for scheduling of missions across the 24-hour day up to 365 days per year. Also, different types of missions will require different numbers of systems. The combat data are the data that allow system casualties to be simulated, and if a system is taken out of action completely, the time to obtain a replacement is modeled. Segments are displayed in the analysis tree below the scenario. So here's my scenario. If I expand that by clicking the plus symbol, I can see that there's 1 segment defined. If I double click on the segment, it opens the description window. So here I can enter the segment name and a description. And below that there are 4 sub-tabs: segment information, operational tempo, combat, and consumables. The segment info has 4 sub-tabs with that one: start, duration, repeat, and stop repeat. From here on the start tab, I set a priority for this segment. The priority tells the set model which segment to release when multiple segments compete for the same system at the same time. The segment with the higher priority gets the available systems first. Note that the lower number in the priority field, the higher its priority. Now, cancellation time, that's what time, if enough systems are not available, after waiting for that amount of time, that segment will be canceled. The next part down here is the start time. So here's where I enter when the segment's going to start. And I have 3 options. I can either just enter a time, I can use distributions, or I can enter an expression. So in this example, our segment is going to start at 0 hours on day 1. The minimum number of systems are not available at that time. IMPRINT will wait exactly the cancellation time, or 0.5 hours, to check once more. If by this time the minimum number of systems are still not available, the segment will be canceled. The next tab is duration. Here I specify the duration of a segment by entering a time manually. Once again, I can either enter it, use distributions, or enter it in expressions. Here we've gone ahead and used a normal distribution, and we specified a mean time of 4 hours with a standard deviation of 0.2 hours. So that means this segment will last approximately 4 hours each time it executes. Under our repeat tab here, we've enabled the repeat option by checking this box. Next, we select an option for manually specifying a repeat interval. Once again, we have enter time, use distributions, or use expression. Here we set it to be a mean time of every 24 hours. So in this case, this segment will repeat once a day. The stop repeat allows you to manually set what time it will stop repeating. Here we've checked the box and we're going to repeat it for 10 times. Now let's look at the operational tempo. So that's the second tab in. Here we specify how many systems to send out and how often. Preventative maintenance checks and services, or PMCS, are any maintenance required before or after a system is sent out. Let's look at the tank line. An attempt to send out at least one tank every 0.17 hours will be made if systems are available. At most, 4 systems can be sent out. A minimum of 1 is always required for the system to be sent, and no PMCS is required. Next is the Combat tab. Combat affects your system availability. It will ultimately also affect your manpower estimates due to the need for maintainers to make system repairs. On this tab, you specify the probability of hit, probability of attrition if hit, replacement time, and repair time. For the helicopter, for every hour the system is in use, there is a 20% chance the system will sustain a hit in combat. There's a 50% chance that the hit will render the system a total loss, and it will take 24 hours to get a replacement or 36 hours to repair. Lastly, let's look at consumables. Based on the numbers entered in this tab, IMPRINT calculates the operational units consumed, either rounds fired, gallons used, or miles traveled, at all times during the model run. Consumables are important because they are parameters on which component failures are triggered. For example, if a cannon tube is estimated to fail every 180 rounds, then we can expect this failure to occur approximately when our system reaches its 12th segment. The failure will then lead to need for maintainers to make repairs, at which point maintenance man-hours start to accrue. The current system, the tank, as selected in this drop-down, will travel 20 miles per hour and will consume 5 gallons of fuel per mile. It's estimated that each subsystem will consume approximately 15 rounds in each segment. We have now gone over the 3 elements of a maintenance model: the warfighters, systems, and scenarios. Now we can execute our model. I recommend you go through a 3-step process to run your model. First, check and edit the execution settings. Second, check for errors. And third, begin the simulation. The execution settings window is opened by clicking the execution settings icon on the toolbar. Once that's open, I can select which scenario I want to execute. And I select my maintenance settings here. I can set the length of run. I can set the number of times to run it. I can set the warm-up period, a random number seed. I can also do things like enable PSF adjustments, set crew limits on or off, set the animation on or off. So that's what I do use the execution settings for. Now, next, let's check for errors by clicking the little check mark on the toolbar. It's going to display any output down in this output window. So here it says I found no errors were found, simulation was created successfully. So now we're ready to run the model. So all we have to do to run it is we click this begin simulation button on the toolbar. When you run your model, the subsystem and scenario data combines with the stochastic maintenance model included in IMPRINT to provide data about the operational readiness of your scenario. So here you can see it's written, writes output and model status to the output window, and it indicates when each run is finished. Running the tank for 10 days took approximately 2.71 real-time seconds, where 240 hours were executed per run, and we ran 10 runs. Now that we've run our model, we can view the built-in reports. There are 22 maintenance model reports available. All reports in IMPRINT are displayed in Excel. The reports are either textual or charts. When the model has completed execution, IMPRINT prepares a number of reports of both detailed and summary measures. In this way, information is available on soldier task performance and on overall system performance. The overall measures reflect the interaction of the soldier performance with all the various factors of battlefield, such as the distance, battle intensity, repair parts availability, maintainer workload, and so on. Let's now go back to IMPRINT and open all the available reports. To access reports, you just select Maintenance Results under the Reports menu. A window will appear that lets you select which reports you want to see, and at the bottom are options for Check All and Clear All. We're going to select Check All and then click the OK button. IMPRINT will then generate the reports in Excel. If any reports need clarification, another box will pop up and ask you for options. To select all, just say OK. When finished generating the reports, as you can see the status down here at the bottom, IMPRINT will open the Excel workbook. For every report, header information is shown at the top. The IMPRINT logo, the name of the report, analysis scenario and system data, and then the actual report data is shown below that. The first report is the maintenance summary report, where summary information regarding every run is shown. You can see the total operating hours, the total maintenance hours, the maintenance hours by system for preventative, corrective, and scheduled, and the maintenance man hours per operating hours. The mean, min, and max are also shown since I've run it 10 times. And you can select any other report by just selecting the tab at the bottom of the workbook. For version 4.6, all of the IMPRINT charts are rendered as Excel objects so that you can edit the chart if desired. Thank you very much for taking the time to view this IMPRINT Maintenance Model Introduction video. My email is listed here on this slide. If you do not already have IMPRINT, you can request it using the really long email on this slide. Happy maintenance modeling!